Proposition 2.5 is a very powerful result that will be used over and over again throughout this course. It says that for random variables x, y, and z, x is independent of z conditioning on y if and only if pxyz can be factorized as axy times byz for all x, y, and z such that py is bigger than 0. Here axy and byz are not necessarily probability distributions. A is a function that depends only on x and y, and b is a function that depends only on y and z. We are going to prove proposition 2.5 in two parts. First, we prove the only if part. Assume that pxy takes the form in definition 2.4. For all x and for all y such that py is bigger than 0, we let axy equals pxy divided by py. For all y such that py is bigger than 0, and for all z, we let byz equals pyz. Thus, we have shown that pxyz is equal to axy times byz, and therefore, the only if part is proved. We note, however, that the choice of axy and byz is not unique. For example, one can as well choose axy equals pxy and byz equals pyz divided by py. Next, we prove the if part of proposition 2.5. Refer to definition 2.4 for x and z being independent conditioning on y. First, we assume that pxyz can be factorized as axy times pyz for all x, y, and z such that py is bigger than 0. Let us highlight this assumption. Then for such x, y, and z, we have pxy equals summation z pxyz, where pxyz is equal to axy times byz by our assumption. Now axy does not depend on z, so it can be moved outside the summation, and we have axy times summation z byz. Similarly, pyz is obtained by summing over all x pxyz, where pxyz is equal to axy times byz. Again, byz does not depend on x, so we can move it outside the summation to obtain byz times summation x axy. Furthermore, y is obtained by summing pyz over all z, and here we use the expression for pyz that we have just obtained, as highlighted in blue. With this expression and summing over all z, we obtain summation x axy times summation z byz, and by our assumption, py is bigger than 0, so it implies that neither of these summation is equal to 0. Now consider the fraction pxy times pyz divided by py. We are going to use the expressions that we have obtained for pxy, for pyz, and for py. Substituting these expressions, we obtain this rather complicated fraction, which in fact is very easy to obtain. What we have done is that we moved this expression over, and then we move this expression over. Now we observe that summation x axy upstairs can be cancelled with the summation x axy downstairs. Now this is possible because we have seen that this summation is not equal to 0. At the same time, we also observe that summation z byz upstairs can be cancelled with summation z byz downstairs. And what is left is axy times byz, which by our assumption is equal to pxyz. And so we have shown that pxyz is equal to pxy times pyz divided by py. And this is precisely the first case in definition 2.4. Finally, we consider the case that py is equal to 0. For this case, we observe that pxyz is lower bounded by 0 and upper bounded by py, which by our assumption is equal to 0. Therefore, pxyz is equal to 0, and this is precisely the second case in definition 2.4. Hence, we have shown that x is independent of z conditioning on y according to definition 2.4.